There was a blackboard in a study in Copenhagen, and on the day its owner died, it still held a drawing. The man was Niels Bohr. The year was 1962, and the drawing chalked onto that board, faint and a little smudged the way chalk always is, was not his own idea. It was a sketch of a small box, a box hanging from a spring with a tiny shutter and a clock inside it. It was a picture that had been drawn in its first form more than 30 years earlier, by a friend, by a rival, by the one person Bohr seemed never quite able to stop arguing with, even after that person had been gone for 7 years. The man who first imagined that little box was Albert Einstein, and so here is where we'll begin tonight. Wherever you are, picture it. A quiet room, books along the walls, the particular stillness of a place where someone has just stopped working forever. And on the wall, still waiting for a reply, a drawing of an argument that had no winner yet. Bohr had been wrestling with it that very week, returning to it, sketching it out again the way you might worry at a loose thread, or replay an old conversation with someone you've lost. He drew Einstein's box on the last day of his life, still answering, still listening to a voice that had gone silent in 1955. That's our story. Two of the greatest minds in the history of the human race, locked for decades in the gentlest, most stubborn disagreement you can imagine, not about politics, not about pride, but about something far stranger, about what reality actually is, about whether the universe underneath everything is solid and certain and knowable, or whether, at its very deepest level, it plays dice. Welcome to the Curious Voyager. It really is lovely to have you here tonight. Before we sink any deeper into this, let me just say, if you find these slow night journeys soothing, a quiet like and a subscribe genuinely help this little channel keep drifting along. Small creators like me really do rely on it, and I'm grateful to every single one of you who's already here. And while you're settling in, wherever you are, whatever corner of the world is dark around you right now, I'd love to know, where are you listening from tonight? What time is it in your part of the night? Leave it in the comments if you feel like it. It's a nice thing, knowing we're all drifting off together, scattered across the planet, under the same strange physics. Now, here is my promise to you, and it's the only one that matters. We are going to move slowly, so slowly. There is absolutely no need to follow every turn of this, no need to grasp every idea, no need to hold a single fact in your hand. This isn't a lecture and there's no test in the morning. If your eyes are already heavy, let them be heavy. If you drift off somewhere in the middle, and I rather hope you do, that's perfectly fine. The story will still be here. Einstein and Bohr will still be arguing whether or not you're awake to hear it. The whole point of tonight is to give your busy mind something gentle and beautiful and true to rest against, like a hand on the rail of a slow-moving train while the rest of you lets go. I'll try not to make this so interesting it keeps you awake, but if it does, well, at least you'll have learned something lovely about the nature of the universe before sunrise. A fair trade, I think. So, get comfortable, let your shoulders drop away from your ears. If there's a lamp still on, that's all right. Leave it glowing soft and gold in the dark. And let's drift slowly back to a room in Brussels in the autumn of 1927. It was October, and in that month, in that city, 29 people gathered for something called the Fifth Solvay Conference. The theme that year was written plainly across the top of the proceedings. Electrons and Photons, which is a quiet, ordinary little phrase for what was really happening in that room. Because what was really happening was that the smartest people alive had come together to decide what the world is made of at the very bottom, where things stop being things and start being something far harder to name. Let that number settle in for a moment, because it's almost difficult to believe. 29 people sat for the conference, and of those 29, 17 had won, or would one day win, the Nobel Prize. 17 out of 29. There has, very possibly, never been another photograph like the one they took. You may have seen it, even without knowing what it was. 3 neat rows of people in dark formal clothes, the men in stiff collars, the few women among them composed and serious. Everyone looking straight ahead the way people did in old photographs, holding still for the long exposure. And nearly every face in that picture belongs to someone whose name is now stamped onto the laws of nature itself. It's a class portrait of the people who rewrote reality. And there, seated right in the front and center, hands folded in his lap, is Einstein. And a row behind him, among the others, is Bohr. The whole future of physics sat down together and posed for a picture, and not one of them, looking at the camera, could have told you how the argument they were about to have would end, because it wouldn't end, not in that room, not in their lifetimes. The answer they were reaching for would not arrive for another 95 years. But I'm getting ahead of myself. Let's slow down again. Let's just sit in that room for a while with these 2 men and get to know them, because the whole story really does come down to the 2 of them, and they could not have been more different. Start with Bohr. Niels Bohr. A large, gentle, deliberate man from Denmark with a heavy head and slow, careful movements and a mind that simply would not stop turning a thing over. If you had to pick the worst public speaker among all the geniuses in that room, it might well have been him. Bohr was, by all the accounts of the people who suffered through his lectures, almost impossible to follow when he talked. He mumbled. He spoke so quietly people leaned in and still couldn't catch it. He would start a sentence, stop, decide it wasn't quite right, and revise it, and then revise the revision, chasing the exact shade of meaning he wanted while his audience drifted somewhere behind him, lost. He thought out loud, and his thinking was a slow, foggy, endless circling. Watching Bohr give a talk was, people said, a little like watching someone try to fold a map in a strong wind. You could see the effort, you could see the care, you just couldn't always see where it landed. But here's the thing about that fog, it wasn't confusion, it was honesty. Bohr mumbled and circled and revised because he refused to say anything cleaner or simpler than the truth would allow. He distrusted a sentence that came out too neat, and when it came to the deep strangeness of the quantum world, the world of the very, very small, he had decided that the truth simply was not neat, that it never could be, that anyone who made it sound tidy was lying, even if only to themselves. And then across the room there was Einstein. And Einstein was everything Bohr was not, at least on the surface. Where Bohr fogged and mumbled, Einstein was clear. Luminously, almost unfairly clear. He had a gift not just for seeing the deep structure of the world, but for saying it, for finding the one sharp image, the one sentence that cut straight through. He spoke in aphorisms, little polished lines that stuck in the memory and refused to leave. He could take the most abstract idea in all of physics and hand it to you wrapped in a picture you'd never forget. A man on a train, a falling elevator, a clock and a ray of light. Where Bohr's thinking wound and doubled back, Einstein's seemed to arrive whole, already shaped, already beautiful. And yet, and here is the lovely irony at the center of everything tonight. For all his clarity, Einstein was, in this particular argument, the one who could not quite let go. He was the one holding on with both hands to an older and warmer idea of how the world ought to work. And Bohr, fogged, mumbling, endlessly hedging Bohr, was the one urging him to let it go, to accept that the universe was stranger and more slippery than anyone had wanted it to be. The clear man wanted certainty. The foggy man had made his peace with mist. Hold on to that, it's the whole shape of the thing. There was a third figure I want you to meet too before we go on, because he stands quietly at the heart of this story, even though his name is less famous. His name was Paul Ehrenfest. And Ehrenfest was the friend of both men, a brilliant physicist in his own right, but more than that, the person who loved them both and stood anguished in the space between them. When Einstein and Bohr went at each other gently but relentlessly, it was Ehrenfest who felt it most. He was the mediator, the one caught in the middle, watching two people he admired more than almost anyone in the world refuse to agree, and unable to bring them together. He wrote letters about these debates, and through those letters we can still feel the ache of it, the sense of a man pulled in two directions by his own affection. Picture him there at the edge of the conversation, hands wringing a little, wishing his two friends would just somehow see the same thing at the same time. Because here is the part that so many tellings of this story get wrong, and I want to set it down carefully and softly before we go any further, like setting a cup down on a table in the dark so it doesn't make a sound. This was not a feud. It would be easy and it would be wrong to imagine Einstein and Bohr as enemies, to picture two men glaring across a room, rivals in the bitter sense, each hoping to humiliate the other. That isn't what this was, not even close. What passed between Einstein and Bohr over all those years was, in truth, one of the great intellectual friendships in the history of science. They respected each other enormously. They were fond of each other, genuinely, warmly fond. Einstein admired Bohr's mind and said so openly in the highest terms. And Bohr? Well, we've already seen how this story ends for Bohr, haven't we? With a blackboard, with Einstein's little box still drawn there on the very last day of his life, 7 years after Einstein was gone. That is not the act of a man who hated his rival. That is something far closer to love, to the way you keep turning over the words of someone you've lost, wishing you could pick the conversation back up, wishing you'd had just one more chance to make them understand, or to be made to understand yourself. This was an argument between friends, the very deepest kind of argument, the kind you can only really have with someone you trust completely, the kind where the stakes feel enormous precisely because you respect the other person too much to dismiss them. Einstein could not simply wave Bohr away because Einstein knew exactly how good Bohr was. And Bohr could never quite rest easy in his own conclusions because somewhere in the back of his mind, always, was Einstein, frowning, unconvinced, drawing another little box, asking another impossible question. They needed each other. The argument was a kind of bond. Two people circling one another for decades around a single question that neither could put down. And what was the question? What were they actually arguing about underneath all of it? Let me give it to you gently, because this is the seed of everything, and we have all night to let it grow. In the years just before that Brussels conference, a new physics had been born. The physics of the very small, of atoms and the particles inside them, and the light they give off. It was called quantum mechanics, and it worked. That was the maddening thing. It worked beautifully. It predicted the behavior of the tiny world with a precision that nothing in the history of science had ever matched. The equations gave the right answers every time, but the picture of reality those equations seemed to demand was deeply, profoundly strange, because quantum mechanics did not say, here is a particle, and it is in this place moving at this speed, and we simply haven't measured it carefully enough yet. No, it said something far more unsettling. It said that until you look, the particle does not have a definite place at all. That the world at its smallest scale is not made of solid little facts waiting to be discovered, but of possibilities, of chances, of maybes, of a kind of shimmering uncertainty that only settles into a single answer at the very moment someone measures it. In the old physics, Einstein's physics, the physics of stars and gravity and the bending of light, the world was definite. Things had properties whether or not anyone was watching. The moon was up there whether or not you looked at it. That was simply obvious. That was what it meant for something to be real. But the new physics whispered that down at the bottom, this was no longer true. That the act of measuring didn't just reveal what was already there. It helped to decide it. That before the measurement, there was no single, definite there to reveal. And to Einstein, this was not just strange, it was unacceptable. It went against his deepest instinct about the universe. An instinct that was almost, though he'd have been careful about the word, religious. Einstein believed the world was lawful, orderly, knowable. He believed that beneath the apparent randomness of the quantum world, there had to be a deeper layer, a hidden machinery, where everything was once again definite and determined. We just couldn't see it yet. He could not accept that chance, real chance, true randomness, sat at the foundation of reality. He could not accept that God, and Einstein used that word to mean the deep order of nature, not a man on a throne, would build a universe on a roll of the dice. And here is where one of the most famous sentences in the history of science enters our story. And I want to give it to you properly, the way it really happened, because the way it's usually told gets it almost right and yet slightly wrong. And the truth is better than the legend. You have probably heard it. God does not play dice. 6 words, and they've come to stand in for this whole vast argument, the way a single photograph stands in for an entire war. But Einstein didn't stand up at a podium in Brussels and shout it across the room at Bohr the way the story sometimes goes. That's the dramatized version, the stage play, and it's worth being gentle and honest about which parts are which. The real moment was quieter and somehow more touching for it. It came in a letter. In December of 1926, before that Solvay conference we've been sitting in, Einstein wrote to his friend Max Born. Born was another of these brilliant minds wrestling with the new physics, and Einstein wrote to him in German, trying to put his unease into words. He wrote that quantum mechanics yielded a great deal, that it accomplished much, but that it hardly brought us any closer, he said, to the secret of the old one. The old one? That was his gentle, half-affectionate name for the deep order behind the universe. And then he wrote the line. In any case, he said, I am convinced that he does not play dice, and that's where it comes from. Not a shouted retort across a crowded hall, but a private letter to a friend, a man thinking aloud on paper, reaching for words to hold a feeling almost too big for them. He does not play dice. The conviction was real, as real and deep as anything Einstein ever felt. The drama, the image of him flinging it across the room, that's just the way we've dressed it up since, because we love a clean story. The feeling underneath, though, was solid as stone. Einstein simply could not believe that the universe, at its heart, was a game of chance. And Bohr, well, there's a reply that has come down to us attached to this exchange, and it's a good one. So good that I almost don't want to tell you the truth about it, but I will softly, because we've promised each other honesty tonight. The line is usually given as Bohr saying gently, Einstein, stop telling God what to do, and it's a lovely answer, isn't it? It captures something true about Bohr's whole position. The idea that it isn't our place to insist the universe behave the way we'd like it to. That perhaps the cosmos is under no obligation to match our intuitions about how reality ought to feel. But I should tell you that this particular line, the exact words of it, the exact moment, that part is uncertain. It's the kind of thing reported by people who knew Bohr, passed along, polished a little with each telling, the way good lines always are. So let's hold it lightly. Let's say it has the right flavor, the true spirit of the man, even if we can't be sure he said it just so. The sentiment was real. The wording is a little bit of myth, and that's all right. Stories carry truth in more than one way. So now you can feel the real shape of it. Two friends, two of the finest minds the species has ever produced. One of them, Einstein, clear and certain, and holding fast to a world that was definite and lawful all the way down. The other, Bohr, foggy and patient, and insisting that the world was stranger than that certainty itself had to be given up, that the act of looking was tangled up with the thing being looked at in a way we could never fully unweave, and neither of them able to convince the other. Not in Brussels in 27, not later, not ever, really, in the years they had left. And what makes it almost unbearably moving, what I keep returning to, the way Bohr kept returning to that blackboard, is that they were both, in their way, partly right. Though neither of them would live to learn exactly how, the universe would take its time answering them. It would let both of these great men go to their graves, still wondering. And then, decades later, long after the room in Brussels had emptied and the photograph had yellowed and the chalk box had been wiped from the blackboard at last, the universe would finally, quietly, give its verdict. But we are a long, long way from that verdict yet. We have a whole night ahead of us. And the next thing Einstein did in the years after Brussels was not to give up. Oh no, Einstein didn't give up. Instead, he began to design little traps. Small, ingenious thought experiments, each one built to catch the new physics in a contradiction, to prove that it couldn't possibly be the whole story. He would arrive at these conferences with a fresh puzzle, a new impossible box, and lay it gently in front of Bohr like a chess move, and Bohr would take it away and fog over it and circle it and lose sleep over it, and come back, somehow, with an answer. One of those boxes, the most beautiful and the most famous of them all, was a box that emitted a single particle of light, a box you could weigh. And it would take Bohr a sleepless night and a borrowed weapon to defeat it, a weapon he would take, of all places, from Einstein himself. But that will come to slowly. Let your breathing settle. There's no rush at all. The box isn't going anywhere, and neither are we. Let me take you back then to the beginning of the picture. Not the box. That comes later. The blackboard. Picture a study in Copenhagen in the autumn of 1962, an old man's room, lived in, full of paper. There are books leaning against books. There is the particular quiet of a place where someone has thought hard for a very long time. And on the wall, a blackboard. Niels Bohr died that November, you see, an old man at last, having spent the better part of his life as one of the architects of the strangest idea humanity had ever stumbled into. And on the day he died, the blackboard in that study still carried a drawing, a careful little sketch of a box hanging from a spring with a tiny shutter and a clock inside it. It was Einstein's box, the light box. A puzzle his old friend had handed him more than 30 years before, in 1930, and there it was, still chalked on the wall, on the last day of Bohr's life. He was, in a sense, still arguing, still turning it over, still answering a man who had been gone for 7 years. I find that almost unbearably gentle when you sit with it. Not two rivals locked in hatred, two friends, and one of them still working at the other's question after death had taken them both off the board. That is the heart of the whole story we're going to drift through tonight. Hold on to that image. the box on the blackboard, because everything else hangs from it, the way the box itself hung from its little spring. Now, before we go any further into the night, let me say a soft, small thing, and then I'll let you settle right back down. If you find a little comfort in these slow journeys, if you'd like more of them waiting for you on the nights you can't switch your mind off, a quiet like and a subscribe genuinely help this sleepy little channel keep going. Small creators like me really do rely on it, and I'm grateful to every one of you who's already here. And while you're drifting, I'd love to know, where in the world are you listening from tonight? What time is it in your corner of the dark? You don't have to do a thing with that thought. Just let it float. And let me promise you the only thing I'll really promise: we are going to go slowly. Achingly slowly, if you like. There is no test at the end of this. You do not need to follow every step. You do not need to remember a single name. You do not need to understand the physics to feel the shape of the story. If you drift off somewhere in the middle of Brussels, and Brussels is exactly where we're going, that is perfectly fine. The argument will still be here. It waited 30 years for an answer. It can certainly wait for you to wake. So, let's go back. Way back before the blackboard, to the moment the two men sat down across a table from each other for the very first time in front of the whole world. The year is 1927, the city is Brussels, and there is a conference. It was called the Fifth Solvay Conference, and the theme that year was simply Electrons and Photons. Now, a conference might sound like the least magical thing in the world. A hotel, some chairs, a long week of people talking. But try for a moment to feel the weight of who was in that room. 29 people had been invited. 29. And of those 29, 17 had won, or would go on to win, the Nobel Prize. Let that settle for a second. 17 Nobel laureates in one room, sitting for one photograph. There is a photograph, you know. It's real, and it's one of the most reproduced images in the history of science. You may even have seen it without knowing what you were looking at. Rows of serious people in dark suits, hands folded, staring out at us across nearly 100 years. And there, in the front row, dead center, sits a man with soft, tired eyes and that great, unruly cloud of hair just beginning to grey. Einstein, the most famous mind on the planet. And behind him, a row back, a heavier, gentler-looking man with a long, thoughtful face. Bohr, the whole future of what we would come to call reality, the question of what the world is actually made of underneath, sat down together and held still for a portrait. They couldn't have known it, but that photograph is a picture of an argument about to begin. And here's the thing about these two men: they could hardly have been more different, not as enemies, as temperaments. Einstein was lucid. He spoke and wrote in clean, sharp, almost poetic lines, the kind of sentences you can carry around in your pocket. He had a gift for the aphorism, for saying the deep thing in the small phrase. When Einstein made a point, it landed like a stone in still water, and you felt the ripple at once. Bohr was, well, the opposite. Bohr was famously, almost legendarily, difficult to follow. He mumbled, he revised himself constantly, mid-sentence, circling back and qualifying and softening, as if no single phrasing could ever quite hold the shape of what he meant. People who attended his lectures sometimes confessed, gently, that they couldn't make out half of what he said. He would fog over an idea, the way breath fogs a cold window, going round and round it, never quite letting it sit still. Where Einstein cut, Bohr clouded, and between them, caught right in the middle of these two enormous opposite minds, there was a third man you should meet, because the whole human warmth of this story runs through him. His name was Paul Ehrenfest. He was a dear friend to both of them, and he played a kind of anguished mediator, a man torn down the middle, watching two people he loved and admired pull in opposite directions over the deepest question there is. It was Ehrenfest who wrote letters home describing the exchanges, who reported what was said across those tables, who felt the strain of it in his own heart. When we glimpse what passed between Einstein and Bohr in those days, very often it's through Ehrenfest's anguished, loving eyes that we're seeing it. So what exactly were they fighting about? And I want to be careful with that word fighting, because it's the word everyone reaches for, and it's a little wrong. There was no animosity here, none. That's the part the loud, hurried versions of this story always get backwards. Einstein and Bohr held each other in deep, genuine affection and the highest respect. Einstein admired Bohr's work openly, warmly. And Bohr, well, you already know how it ends for Bohr, don't you? With a drawing of his old friend's puzzle still on his wall on the day he died. That is not how you remember an enemy. That is how you remember someone you loved arguing with. So set aside any picture of two men shouting red-faced across a hall. What you should imagine instead is something much quieter and honestly much rarer. A gentlemanly disagreement between friends conducted with enormous courtesy that simply happened to be about the nature of all of reality and simply happened to last on and off for the rest of their lives. A decades-long conversation, the longest, deepest argument two friends have perhaps ever had. Now, somewhere in all of this, you've almost certainly heard one phrase. Maybe it's the only thing you've heard about Einstein and the quantum. 5 little words. God does not play dice. It's everywhere. It's on posters and mugs and the front of 1,000 videos. And like most things that get worn that's smooth from handling, the truth of it is a little softer and a little more interesting than the slogan. Einstein never stood up at a podium in Brussels and declared it like a thunderclap. That's the staging we've added later because it makes a better scene. What actually happened is gentler and, I think, more touching. In December of 1926, and so even before that famous conference, Einstein sat down and wrote a letter, a private letter in German to his friend Max Born, and in it he was wrestling on paper with this new physics that troubled him so. He wrote that the theory yields a great deal, yes, but that it hardly brings us any closer to the secret of, as he put it, the old one. And then the line. In any case, he wrote, I am convinced that he does not play dice. That's where it comes from, not a shout across a hall, a quiet line in a letter to a friend, written by a man genuinely unsettled in the soft privacy of his own correspondence. The slogan is a compression of that, true to the feeling, but flattened the way a real thing always flattens when a million hands pass it along. And there's a famous reply too. The story goes that Bohr, hearing this, answered, Einstein, stop telling God what to do. It's a lovely line. It's repeated everywhere. But I'll be honest with you, here in the dark, because honesty is part of the calm. We don't actually know that he said it, or said it quite that way, or when. It's reported by people close to Bohr. It has the right flavor. It sounds exactly like the kind of warm, exasperated thing one friend says to another. But as a verbatim quote, pinned to a moment, it's uncertain. A bit of true feeling chalk dust drifting down through the years. So here are two friends then. One who could not believe that the universe at its very bottom runs on chance, that God, the old one, would roll dice with the world, and one who was coming to believe exactly that and more, and was prepared to follow the strange new physics wherever it led, however uncomfortable the destination. That was the disagreement. Not who was smarter, not whose math was right. Something far deeper and far quieter than that. And so we move a little further into their argument, which is where it gets quietly beautiful. Because Einstein did not simply write a letter and leave it there. He was too precise for that, too committed. If he believed the theory was missing something, he needed to show it was missing something, to find the crack in the floor, to put his finger exactly on the place where the new quantum mechanics, for all its impressive predictions, failed to be a complete account of what was really happening. And he had a method for finding cracks. He had always had it. He called them thought experiments, Gedanken experiments in German. Not experiments you run in a laboratory, but experiments you run entirely in the mind. Careful, clean, controlled scenarios that isolate one principle and press on it until it either holds or gives way. He had been doing this his whole life. It was how he had arrived at special relativity in the first place, by imagining himself riding alongside a beam of light and asking what he would see. Not a machine, not a laboratory, just a mind and a question, and the willingness to follow the reasoning wherever it went. And now, in the late 1920s and into the 1930s, he turned that same method on quantum mechanics. He came to each Solvay Conference, the gatherings where the whole physics community assembled, where Bohr would be, where the debate could happen in person, armed with a new thought experiment, a new puzzle, a new crack to press. The target of these thought experiments was a principle that had emerged from the quantum revolution just a year before the 1927 Solvay. Werner Heisenberg, a young German physicist, had worked out something in 1927 that would become one of the most famous and most misunderstood results in all of science: the uncertainty principle. And what it says at its core is this: there are pairs of properties in nature, pairs of measurable things about a particle that cannot both be precisely known at the same time. The more precisely you nail down one, the less precisely you can know the other. The two most famous such a pair are position and momentum. The more sharply you locate a particle, the more you pin down exactly where it is, the less you can say about how fast it is moving and in what direction. And the same is true in reverse. The more precisely you know the momentum, the more the position blurs out. Now, it is very easy to hear that and imagine that this is just a practical limitation, that the uncertainty is about our instruments being clumsy, that particles nudge each other when we try to measure them, that in principle a perfect experiment with perfect equipment would give us perfect information. That is not what Heisenberg showed. The uncertainty is not in our tools. It is in nature itself. Position and momentum are not both sharply defined at the same moment, even before you look. The particle does not secretly have a precise position and a precise momentum that you are simply failing to find out. Both things are genuinely irreducibly blurry at the quantum level, and the fuzziness of one is mathematically tied to the sharpness of the other. Einstein found this deeply, genuinely troubling. Not because the mathematics was wrong, he could see that the mathematics worked, but because it seemed to say that there are facts about nature that nature herself does not have settled until you look. And that to Einstein sounded like a universe running on dice, a universe whose behavior at the smallest scales was not determined by underlying causes but by something that amounted to pure chance. And that was precisely what he could not accept. So he designed thought experiments to show that the uncertainty principle could be beaten, that if you were clever enough, you could find a way to measure both things, position and momentum, or the other famous pair, energy and time, with precision enough to violate the principle. If you could beat the uncertainty principle, even in principle, even in a thought experiment, it would show that the principle was not fundamental. That it was, as Einstein suspected, a temporary limitation, a fog over the real deterministic machinery beneath. He brought these experiments to Solvay. and each morning, the story goes, he arrived at breakfast with a new one. Something careful, something elegant, something that seemed to have found a way around the principle. And each evening, Bohr, talking with others, working it through, sometimes barely sleeping, would come back with an answer, would find the hidden flaw, the overlooked effect, the place where the thought experiment examined carefully enough did not actually do what Einstein claimed. And back and forth it went, through the conferences, through the years, through the breakfasts and the evening walks. Paul Ehrenfest, who was a close friend to both of them and who attended these gatherings and watched them argue, wrote in a letter that he was almost losing his mind, that watching the two greatest figures in physics disagree so fundamentally was both exhilarating and quietly heartbreaking. He loved them both. He could not bear for either of them to be wrong. But the third Solvay in 1930 brought a thought experiment that was different. This one was serious enough that it shook things, at least briefly. Einstein arrived with what became known as the photon box, or the light box, and it was, on the surface, remarkably simple. Imagine a box, a small sealed box perfectly isolated from the outside world. Inside it is a quantity of radiation, photons, particles of light, and the box has a shutter in its wall. The shutter can be opened for an extremely precise, extremely brief interval, allowing exactly one photon to escape. Now, and here is Einstein's move, you weigh the box. You weigh it very carefully before the shutter opens, and then very carefully again after the photon escapes. The difference in weight gives you the mass of the photon that left, and because of Einstein's own equation, E equals mc squared, energy equals mass times the speed of light squared. If you know the mass, you know the energy. You can measure the energy of the photon precisely, and separately you can control the shutter with a clock, opening it for a precisely known duration at a precisely known time. So you know when the photon left with precision. Energy measured precisely from the weight, time of emission controlled precisely by the clock. Two things, energy and time, that are supposed to be one of those complementary pairs, one of those pairs that cannot both be known sharply at once. And yet here, Einstein seemed to be saying, you have measured both. You have beaten the energy-time uncertainty relation. You have found the crack. It was, by most accounts, the most serious challenge Einstein had brought. When he presented it at the 1930 Solvay, the initial response from the gathered physicists was quiet, uncertain. Bohr, reportedly, was visibly troubled. Ehrenfest's letters from that conference suggest that Bohr had no immediate answer, that he left the room still working on it, still turning the puzzle over, still looking for what Einstein had missed. It seemed for a moment that Einstein might have found it, the loophole, the crack in the new physics. And then Bohr went away and thought, all through the evening, into the night. By the next morning, the story carries the particular texture of a sleepless night discovery, though we hold the exact details as part of the historical atmosphere rather than certainty. By the next morning, he had an answer. And the answer was not what anyone expected. The answer was Einstein's own theory. Bohr's insight was this: to weigh the box, to measure the difference in mass before and after the photon escapes, you have to actually perform a measurement. You cannot simply know the weight abstractly. In a real thought experiment, carried through with physical rigor, the way you weigh something is by hanging it on a spring scale and letting it settle and reading the position of a pointer. The box is suspended, it shifts up or down as the photon leaves and the mass changes. You read the pointer position before and after, but here is the problem, and it is a problem that comes entirely from Einstein's own general theory of relativity. The box, hanging on a spring, moves in space when you weigh it. It shifts up or down, and Einstein himself had shown that a clock's rate depends on its position in a gravitational field. A clock lower in a gravitational field, sitting deeper in a gravity well, runs more slowly than one higher up. This is gravitational time dilation, and it is one of the results of general relativity, the theory Einstein himself had completed in 1915. The clock on the box, after the box shifts in the gravitational field during the weighing, does not run at exactly the same rate as it did before. And that change in rate, that tiny, inevitable blurring of the clock introduced by the gravitational shift during the weighing, introduces exactly the uncertainty in time that the energy-time relation requires. The more precisely you weigh the box and the more precisely you pin down the energy, the more the box must shift to allow that precision, and the more that shift muddles the clock, and the more uncertain the timing of the photon's emission becomes. Exactly as the uncertainty principle demands. Einstein's own relativity restored the principle that Einstein's thought experiment had seemed to defeat. Bohr used Einstein's theory to save the theory Einstein was attacking. The elegance of that is worth sitting with for a moment, there in the quiet. A man who had spent years convinced that quantum mechanics was missing something fundamental, that it must be incomplete, that the uncertainty principle was a temporary fog over a deterministic reality, that man had also spent years developing the general theory of relativity, one of the deepest and most beautiful structures in all of science, and his old friend, his gentle opponent, took that structure and turned it around, held it up to the lightbox thought experiment, and showed that the two fit together, that they cohered, that Einstein's own deepest achievement, his theory of gravity and space-time, was the very instrument that defended the new quantum world against his objections. You can almost feel the texture of that reversal. Einstein, that particular morning, receiving Bohr's argument, understanding it. He was too good a physicist not to understand it, too honest not to recognize when an argument was right. He accepted that Bohr had found the flaw. The lightbox was closed. The thought experiment did not succeed. Bohr's answer was correct. And yet Einstein was not satisfied, not because he thought Bohr's answer was wrong. He didn't. But because to him, the correct answer felt like it had come too easily, had papered over something that was still genuinely wrong. The uncertainty principle could not be beaten in practice. Fine. But the issue for Einstein was not about practice. It was about what the theory was actually saying about the nature of reality. It was about whether quantum mechanics was telling a complete story or not, whether the fog, even if real and unmovable, was all there was, or whether it was covering something. Because here is the thing that sat at the center of Einstein's discomfort, and that he was, through these years, slowly finding the language for. The uncertainty principle does not just say that we cannot measure things precisely. It says something stronger. It says that certain properties of a particle are genuinely not defined until a measurement is made. Position is not sharp, even in principle, even in nature itself, until you look. The particle is not secretly sitting somewhere precise, and you are simply failing to find out where. According to quantum mechanics, the question of where the particle is does not even have a sharp answer until the moment of measurement. And for Einstein, that was the real problem, not the mathematics, not the practical limitations, but the claim, implicit in quantum mechanics as Bohr and Heisenberg understood it, that the universe at its base level does not have definite facts until something interacts with it to reveal them. That reality is, in some sense, incomplete until it is observed. That the moon, as he would later put it, is not there when nobody is looking. He could not believe that. It struck him not just as physically wrong, but as philosophically intolerable. The universe, for Einstein, was not a stage on which properties materialized into existence when observed. It was a structure with definite facts, definite values, whether or not any human or instrument ever looked. What we could measure was a separate question from what existed. And if quantum mechanics was saying otherwise, then quantum mechanics was not finished. It was a provisional tool, a very good one, but not the final word. There was something else at play too. A deeper intuition, one that would become his next and most serious objection. Einstein was troubled not just by the blurriness of individual particles, but by what the theory implied when you consider two particles together. When two quantum systems interact and then separate, quantum mechanics describes them afterward with a single, joint description, a combined state, rather than giving each particle its own independent description. The properties of one particle are not independent of the properties of the other, even after they have moved apart, even across large distances. If you measure something about one, the mathematical description of the other seems to update, instantly, simultaneously, without any signal traveling between them. That bothered Einstein enormously. More than the uncertainty principle, more than the blurriness of individual particles, this bothered him. Because his own special theory of relativity back in 1905 had established something that he regarded as fundamental. Nothing can travel faster than light. Information, influence, causal connections, they all have a speed limit. The universe is arranged so that causes and effects are properly separated in time. What happens here cannot instantly affect what happens there, because instant is not even a well-defined concept across space in a relativistic world. And yet quantum mechanics seemed to be saying that two particles, once they had interacted, remained somehow connected. That what you chose to measure about one had immediate implications for the other, regardless of the distance between them. If you measure a particle here and find it has a certain property, the companion particle over there instantaneously is described as having a corresponding property. No signal, no time. Just a correlation that seemed to reach across space as if space were not even there. Einstein had a name for this that he used in letters to friends. He called it, in German, spukhafte Fernwirkung, spooky action at a distance, a phrase that captures exactly the quality of the thing that troubled him, ghostly, reaching, refusing to respect the boundaries that his own relativity had so carefully defined. He wrote the phrase in a 1947 letter to Max Born, and it is one of those rare moments where a physicist's private language leaps off the page and into history. Spooky action at a distance. It sounds like something from a campfire story, but it is precise physics and it points to a precise problem, and Einstein did not use it as a dismissal, he used it as a diagnosis. He believed the answer was that particles carry hidden information, that when two particles interact and separate, they are not truly entangled in some mystical sense, they simply each carry a set of predetermined values set at the moment of interaction, and those predetermined values account for the correlations you see when you later measure them. Like a pair of gloves separated into two boxes and shipped to opposite ends of the world. If you open one box and find a left glove, you know immediately that the other box contains a right glove. No mystery. No connection. Just information that was already settled when the boxes were packed. The correlation is real but classical. The gloves knew, so to speak, from the beginning. These predetermined values that the particles would carry, waiting to be revealed by measurement rather than called into being by it, were what would later be called hidden variables. Variables that quantum mechanics did not describe, that is, hidden from the theory, but that Einstein believed must be there, doing the real work underneath the probabilistic fog. That was the idea forming in his mind through the early 1930s. The thought experiments at Solvay had not succeeded in cracking the uncertainty principle. Bohr had answered each one, but the deeper question, the question of completeness, the question of whether quantum mechanics was telling the whole story or only a carefully constructed partial story, the question was still entirely open. And in 1935, Einstein found a new and sharper way to press it. He was at the Institute for Advanced Study in Princeton by then, having left Germany in 1933, when the political world had become something he could no longer inhabit. Two colleagues were working with him there, Boris Podolsky, a Russian-born American physicist, and Nathan Rosen, a young American. Together, in 1935, they submitted a paper to the journal Physical Review. The paper's title was stated as a question calmly and precisely. Can quantum mechanical description of physical reality be considered complete? Not is quantum mechanics wrong, not is quantum mechanics inaccurate. Complete. That was the word. They were not attacking the predictions of quantum mechanics. They were not saying the mathematics fails. They were saying something more careful and more cutting, that quantum mechanics might be making the right predictions and still not be telling you everything. That a theory can be empirically successful and still be incomplete, still be missing variables, still be failing to describe a layer of reality that is genuinely there. The argument in the EPR paper, as it has come to be called by the initials of its three authors, goes like this. Imagine two particles that interact and then separate. Quantum mechanics gives them a joint description. They are entangled. Now you make a measurement on one particle, far from the other. You choose what to measure, perhaps the position, perhaps the momentum. Based on your result, you can predict with certainty what the corresponding measurement on the distant particle will find. You can predict it without touching the distant particle, without sending it any signal, without interacting with it in any way, which means, and here is the core of the argument, that the distant particle must already have that property. It must be real, it must be determinate, it must be an element of reality, in the paper's careful language, because you can predict it with certainty and without disturbing it. But quantum mechanics does not assign that property a definite value before the measurement is made. Quantum mechanics says it is indefinite, blurry until measured. So quantum mechanics is missing something. The element of reality is there, it is real, it exists before the measurement, and quantum mechanics does not describe it. Therefore, quantum mechanics is incomplete. It was a precise argument, clean, careful. Not the protest of someone who found quantum mechanics distasteful, though perhaps some of that was there too, but a logical argument with a logical structure that you had to engage with on its own terms. And it shifted the debate, because now it was not just about thought experiments pressing on the uncertainty principle. It was about the logical structure of the theory itself, about what complete even means, about what it means for a property to be real. The paper made a wave. In the physics community, it was taken seriously in a way that generated something close to alarm in Bohr's camp. Bohr himself, by multiple accounts, dropped most of what he was working on and spent weeks writing a reply. His reply appeared in the same journal, Physical Review, in the same year, 1935, with the same title, which gives you a sense of how direct an engagement it was. Bohr answering Einstein's question with Einstein's own question, as if to say, here is the question and here is why I have a different answer. Bohr's reply was careful and many people have found genuinely difficult to follow. He was not the clearest writer, but the substance of his answer was this. The EPR argument assumes that you can speak of the distant particle's properties as existing, as being elements of reality, independently of whatever measurement arrangement you choose to use. It assumes that the particle over there has its own definite values, separate from any experimental context, separate from whatever apparatus might be set up to examine it. But in quantum mechanics, as Bohr understood it, with the principle he called complementarity, that assumption is not valid. You cannot separate the particle from the measurement. The experimental arrangement, the choices you make about what to measure and how, are not external to the system. They are part of it. What you call the particle's properties is always already shaped by the context in which you choose to examine it. Position and momentum are not two things the particle has independently. They are two complementary aspects that only come into meaning relative to specific, mutually exclusive measurement choices. So the EPR argument, Bohr was saying, contained a subtle flaw, not a mathematical flaw, a conceptual one. Its notion of elements of reality, properties that exist independently of measurement, was importing a classical assumption into quantum territory where that assumption does not hold. The particle's properties are not separate from the experimental arrangement that reveals them. There is no fact of the matter about the distant particle's position or momentum that exists before you decide which one to look for. It was a philosophical difference at its heart. Einstein believed in what we might call realism, the idea that the world has definite facts independent of observers. He believed in what we might call locality, the idea that what happens here cannot instantaneously affect what happens there. Together, these two commitments gave him a framework for what a complete physical theory should look like, and quantum mechanics, by his lights, fell short of it. Bohr's complementarity said, give up the classical notion of observer-independent reality at the quantum level, and the paradoxes dissolve. The uncertainty is not a veil over something more definite. It is the thing itself. Neither man convinced the other. The paper exchanges were civil, thorough, utterly inconclusive. Einstein remained unconvinced by complementarity. Bohr remained convinced that EPR, for all its precision, had smuggled in an unjustified assumption. And the rest of the physics community, watching all of this, mostly arrived at a particular and very human conclusion. They concluded that the debate was interesting, but perhaps ultimately not decidable by physics. That the question of whether quantum mechanics was complete in Einstein's sense, of whether hidden variables were real, of whether the universe had definite underlying values or genuinely probabilistic fundamental behavior, these were philosophical questions, questions of interpretation, questions that experiments might never settle because they were not questions about predictions, but about what lay behind predictions. There was even a name for this conclusion. It was sometimes called the shut up and calculate approach. Don't worry about the interpretation. Don't worry about what quantum mechanics means. Take the formalism, use it, get the answers, build the technology. The theory works, the rest is metaphysics. Whether Einstein or Bohr was right about the nature of reality, that question, it was generally agreed, was not one for the laboratory. And there is a particular kind of tiredness in that conclusion. A reasonable tiredness. The debate had gone on for nearly a decade by the time the EPR paper landed, and Bohr replied, and the letters went back and forth, and the conferences receded into memory. Both men were aging, the world around them was changing in terrible ways. The rise of fascism, the coming war, the bomb. Physics had urgent, terrible practical work to do, and the question of whether the universe had definite pre-existing values or not, whether God played dice, felt, however deeply Einstein cared about it, however real the intellectual stakes were, like something that might have to wait, like something that perhaps could only wait because no experiment could reach it. Meanwhile, there was one more voice in 1935 that deserves a quiet moment here. Erwin Schrödinger, the Austrian physicist who had given quantum mechanics its central equation, the equation that describes how quantum states evolve over time, was also reading the EPR paper and thinking about what it implied. And in a series of papers also published in 1935 responding to Einstein and Podolsky and Rosen, he did something important. He gave the phenomenon a name. He called it, in German, Verschränkung, entanglement. The term is in the English now, we have forgotten it was a translation, but it was Schrödinger who reached for that word. Entanglement, the way two things are woven into each other so that you cannot describe them separately, and said that this Verschränkung was not a quirk or an edge case of quantum mechanics. It was, he wrote, the characteristic trait of quantum mechanics, the thing that most sharply distinguished it from classical physics, not a small technical feature, the heart of it. He also wrote in that same burst of work the thought experiment with the cat, a cat inside a sealed box with a quantum device that might or might not trigger a mechanism that might or might not kill it, so that until you open the box, the cat is, in some sense, neither alive nor dead, its fate entangled with a quantum event that has no definite outcome. It is a famous image, and it is a genuinely useful one for illustrating how strange quantum superposition becomes when you scale it up to the everyday world. But I want to be honest with you about where it sits in this particular story. The cat is Schrödinger's illustration of a problem, not the problem's resolution. It was a reductio, a way of making the strangeness visible, of saying, look, if quantum superposition is really real, here is where it leads, and does that seem right to you? It is not the center of the Einstein-Bohr argument, which was specifically about entanglement, about non-locality, about hidden variables. The cat is a visitor to that argument, not its heart. It will not be our spine tonight. The spine is something quieter. It is two men, and between them a question so deep they both came to believe it could not be answered in their lifetimes. Maybe not in any lifetime. Maybe the question of what reality actually is underneath the quantum formalism would remain forever beyond the reach of any instrument anyone could build. A permanent open wound in the foundations of physics, tended carefully, never healed. Einstein lived until 1955. He never stopped thinking about it. He continued to write and to correspond and to probe, looking always for the place where the theory was revealing its incompleteness, looking for a way to find the hidden variable, the deeper level. He never found it. Bohr lived until 1962. He never stopped thinking about it either, never stopped refining his articulation of complementarity, never stopped believing that the question EPR raised had been answered, and that people simply had not yet fully understood his answer. And then something happened that neither of them lived to see. In 1964, a physicist named John Stuart Bell sat down at CERN in Geneva and did something that transformed the debate entirely. He took a question that the physics community had agreed was philosophical and untestable. The question of whether particles carry hidden variables, the question at the heart of the Einstein-Bohr disagreement, and he showed that it was neither. He turned it into mathematics, and the mathematics gave a number you could measure, a number that quantum mechanics and local hidden variable theories, Einstein's preferred kind, predicted differently, not just qualitatively differently, quantitatively, precisely, measurably differently. Bell was from Northern Ireland, trained in Belfast, and he had come to CERN as a particle physicist. But he was also someone who had never been comfortable with the standard dismissal of the interpretation problem, never satisfied with shut up and calculate, never content to leave the foundations unexamined. He had thought carefully about EPR, about hidden variables, about what it would mean for the world to work the way Einstein hoped it worked. And in 1964, working on his own time, almost as a side project, he published a paper in a journal called Physics, not one of the famous journals, a relatively new and not widely read one, called On the Einstein-Podolsky-Rosen Paradox. The paper contained what we now call Bell's theorem, and what it proves goes something like this. If the world is locally realistic, if particles carry hidden, predetermined values, and if measurements on one particle cannot instantly influence the outcome of measurements on another distant particle, then there are mathematical limits on the correlations you can observe between measurement results on pairs of entangled particles. These limits are what Bell's inequality describes, a precise mathematical bound, a number, a threshold that any locally realistic theory must stay within. Quantum mechanics, Bell showed, predicts correlations that violate that bound. Quantum mechanics says the correlations between entangled particles are stronger than any locally realistic theory can produce. not a little stronger, distinctly, measurably, calculably stronger. If you do the experiment, if you actually take pairs of entangled particles, measure them, and compare the statistics, you will get a number. And if that number exceeds Bell's bound, local realism is ruled out. Not disfavored, not challenged, ruled out experimentally by a number. The philosophical question had become an experimental one. The 30-year stalemate had an escape route. Bell himself was, by multiple accounts, sympathetic to Einstein's intuition. He hoped local realism was true. He wanted there to be hidden variables, wanted the universe to have definite underlying facts, wanted Einstein's discomfort with quantum mechanics to be vindicated by nature rather than dismissed by fashion. His theorem was not written as a celebration of quantum mechanics. It was written, in a sense, to give Einstein's hope its best possible chance, to set up the question in the sharpest possible form, so that if an experiment were done, and if the results came back within Bell's bound, that would be genuine, solid evidence for local realism, for hidden variables, for the kind of universe Einstein had imagined. He was handing nature the chance to prove Einstein right. As it turned out, nature had other plans, but the experiment still had to be done. And the theorem, published in that quiet journal in 1964, did not immediately shake the world. It was noticed slowly by a small number of people who cared deeply about foundations, who were willing to work in an area that most of their colleagues considered peripheral. For years, the experimental machinery to test it did not exist. The techniques for reliably producing and measuring pairs of entangled particles, entangled photons in particular, because light is easier to work with than massive particles over distances, those techniques had to be built, refined, improved. It was not until the early 1970s that the first real test was performed. John Clauser, an American physicist, had read Bell's paper and recognized immediately what it meant. He had to fight for the resources to test it. The foundations question was still considered slightly disreputable, not real physics, a hobby for people who couldn't let go of an old philosophical quarrel. But with Stuart Friedman at Berkeley, he performed an experiment in 1972 using photons from calcium atoms. The photons were entangled, their polarizations measured, the statistics collected and analyzed. The results violated Bell's inequality. Quantum mechanics was right. Local realism took its first experimental blow. But there were loopholes, not in the sense of cheating, in the precise technical sense that an experiment that does not close every gap between what you observe and what the theorem requires leaves open the possibility that a locally realistic theory could still, in principle, produce the results you saw. One loophole was the locality loophole. If the measurement settings on one side of the experiment could somehow influence the other side, if there was time for a signal to travel between the two detectors, then you had not truly isolated the particles from each other. The experiment was not conclusive in the way that was needed, and this is where Alain Aspect enters the story. Aspect was based in Orsay, France, at the Université Paris-Sud. He was a young physicist still completing his doctorate, and he had gone to see John Bell in person before beginning his experiments. Bell asked him, perhaps half seriously, whether he had a permanent position, because experiments like this, at the time, were still the kind of thing that could quietly end a career. Aspect said he was not worried, and then he went and did the experiments anyway, which tells you something about the kind of person he was. What Aspect understood, what he had thought through very carefully, was exactly which loophole mattered most, the locality loophole. And to close it, he needed to do something that no previous experiment had done. He needed to change the orientation of the polarizers, the devices that measure which direction the photon's polarization points, while the photons were actually in flight, while they were traveling through the air toward the detectors. Not before the photons were sent. not after they arrived. During, mid-flight. The window of time involved was so small it seems almost conceptually impossible to act within it, and yet that is precisely what the experiment required. If the settings were chosen after the photons left their source, then there was simply no time for any signal, traveling at the speed of light or slower, to carry information from one detector to the other. The two ends of the experiment would be, in the precise technical language of physics, space-like, separated, causally disconnected in the sense that no physical influence could bridge the gap in time. Aspect's experiments performed between 1981 and 1982 used entangled photons produced by calcium atoms that had been excited by lasers. The photons flew in opposite directions toward detectors roughly 13 meters apart. And while they were in flight, the measurement settings were switched rapidly, using acousto-optical switches that could flip orientation in nanoseconds. The photons had no opportunity to coordinate their behavior based on information about the detector settings, because the settings were not fixed until after the photons were already traveling. And yet when the results came in, the correlations were there. The quantum mechanical predictions held. Bell's inequality was violated clearly, decisively, with enough statistical confidence to be taken seriously by even the most cautious experimentalist. Local realism lost again, but this time the locality loophole was closed. Sit with that for a moment, because it is genuinely strange. Two photons produced together flying apart. The moment of measurement, the choice of how to measure each one, made only after they have already parted ways. And still, when you compare the results, there is a correlation that no locally realistic theory can produce. No signal passed between them. No hidden instruction was carried along. And yet they are connected in some way that refuses to fit inside the framework Einstein had hoped to preserve. Aspect published his results, and the physics community took notice. The experiments were not definitively loophole-free. There were still technical gaps that a determined skeptic could point to, but the evidence was growing very hard to dismiss. Quantum mechanics was not just mathematically successful, it was tracking something real about how the world behaves when you push it into the corner Bell had designed. And through all of this, John Bell watched. He had hoped, in some quiet part of himself, that the experiments would vindicate Einstein, that the correlations would obey his inequality and local realism would survive. He had turned Einstein's intuition into arithmetic precisely to give it a fair test, to give it the best possible chance, and the experiments kept returning the same answer. Bell wrote and lectured and refined his ideas about what the results meant for decades, becoming one of the most thoughtful voices on the interpretation of quantum mechanics. He never stopped being troubled by what he had proved. He died in 1990, still arguing, still not entirely at peace with the universe his theorem had helped to reveal. But before we arrive at the final chapter, and before we get to the 2022 Nobel Prize and the last word the universe offered on this argument, we should go back to 1935, because the story of how we got here begins not with Bell and not with Aspect, but with a paper. A quiet, careful, devastating paper published in May of that year in the journal Physical Review. 3 names appeared on it: Albert Einstein, Boris Podolsky, Nathan Rosen. And its title was a question: can quantum mechanical description of physical reality be considered complete? It is worth pausing on that title for a moment, because it is so carefully chosen. Einstein was not claiming quantum mechanics was wrong. He was not saying that its predictions were incorrect. He knew perfectly well that they matched experiments with extraordinary precision. What he was asking was something subtler and in some ways more unsettling. Even if the predictions are right, is the description adequate? Is there something the theory is leaving out? Is there a deeper layer of reality that quantum mechanics cannot see? The paper's argument was built on a definition. Einstein, Podolsky, and Rosen began by proposing what they called a criterion for physical reality. If you can predict with certainty, without disturbing a system in any way, the value of some physical quantity, then there exists, they said, an element of reality corresponding to that quantity. This seems almost self-evidently reasonable. If I can tell you with complete certainty before I look what color a marble is, then the marble has a color. It is not something I create by looking. It is there, waiting. Now consider the following situation which EPR laid out with careful precision. Imagine two particles that have interacted in the past and are now flying apart from each other. Quantum mechanics says that the total angular momentum of the pair is conserved. It is fixed. But it does not say anything definite about the individual angular momentum of either particle. Each one is in a superposition of possible values. Only when you measure one of them does the quantum description specify a definite value for that particle. And at that moment, the other particle, however far away it is, must have the complementary value. If one is measured and found to be spinning up, the other is instantly specified as spinning down. EPR's argument was this: if the two particles have flown far enough apart that measuring one cannot physically reach the other in time, then the measurement of the first particle cannot have disturbed the second, and yet you can predict with certainty the value of the second particle's spin. By their criterion, that value must correspond to an element of physical reality. But quantum mechanics does not assign any definite value to the second particle before measurement. The theory says there is no fact of the matter until a measurement is made. Therefore, EPR concluded, quantum mechanics does not give a complete description of physical reality. There is something missing. The theory is incomplete. The argument is not that quantum mechanics is wrong. It is that quantum mechanics is a partial map of a territory it does not fully chart. Einstein's preferred resolution was elegant in its simplicity. The two particles, he believed, carry predetermined values all along. Values hidden from the theory as it currently stands, but real nonetheless. When they are produced together, they receive complementary instructions, like two envelopes sealed at the same time and mailed to different cities. When you open your envelope, you know immediately what the other envelope contains, not because opening yours affected the other, but because both were packed at the source. The correlations are real, they exist, but they do not require any mysterious connection between the particles after separation. They were written in at the beginning. This is local realism. Local because causes propagate locally. They cannot reach across space instantaneously. And realism because physical properties have definite values independent of whether you measure them or not. Einstein was not being stubborn or sentimental. He was defending something that had seemed, until quantum mechanics arrived, to be the common ground of all physical reasoning, that the world exists in a definite state whether you are looking at it or not. What Einstein could not accept, what he called, in a 1947 letter to Max Born, spukhafte Fernwirkung, spooky action at a distance, was the alternative. The quantum mechanical alternative, which says that the particles do not carry predetermined values, and that measuring one genuinely instantly affects the description of the other, no matter how far apart they are. This seemed to him to violate everything he had built. The whole framework of special relativity is built on the idea that causes propagate at the speed of light, or slower. Instantaneous influence across any distance, however the technical details are arranged, seemed to Einstein like an assault on the foundations. He was not wrong to be alarmed. The alarm was appropriate. The question was whether the alarm pointed toward a flaw in quantum mechanics or toward a genuine, irreducible feature of the universe. The EPR paper landed in the physics community like a very polite grenade. Everyone read it. Almost everyone had a reaction to it. And Erwin Schrödinger, who had been corresponding with Einstein about these ideas, responded almost immediately with something that deepened the strangeness rather than resolving it. Schrödinger, in a series of papers in 1935, introduced a word for the phenomenon EPR had identified. He called it Verschränkung, entanglement. The word means something like interlocking or intertwining, the kind of crossing over you see in braided things in fingers laced together, and he made a claim about it that was not shy at all. Entanglement, Schrödinger wrote, is not one of the features of quantum mechanics. It is the characteristic trait, the thing that makes the theory what it is, the thing that distinguishes it most sharply from any classical picture of the world. It is worth letting that sit for a moment. Not a curiosity, not a corner case. The characteristic trait. Schrödinger saw, even in 1935, that this was not an embarrassing detail that a better theory would iron out. It was the center. And it was in the same burst of work in 1935 that Schrödinger also introduced his famous cat. The cat in the box, simultaneously alive and dead until you open the box and look. The cat is often treated as the heart of the quantum mystery, and it gets more attention than almost any other thought experiment in physics. But here it is worth keeping it in its proper place. The cat is an illustration of a separate, though related problem, the measurement problem, the question of why superpositions seem to collapse into definite states when large-scale systems are involved. That is a deep and still unresolved question. But the cat was Schrödinger's way of dramatizing that problem. It was not aimed at EPR directly. The entanglement was the thing he was most interested in, and the cat, magnificent and disturbing as it is, was a kind of amplifier, a tool to make the strangeness visible at the scale of something you could actually open a box and look at. Schrödinger, in those 1935 papers, sided with Einstein in feeling that something was deeply unsatisfying about the quantum picture. He did not want to accept entanglement as a bedrock fact any more than Einstein did, and yet he had named it precisely and memorably, and his naming would turn out to matter enormously later on. Bohr's response to EPR came in the same year, in the same journal, Physical Review, and with remarkably the same title. Can quantum mechanical description of physical reality be considered complete? It is a very Bohrian gesture, responding by repeating the question back, as if to say, yes, let's really look at this question properly. Bohr's answer was subtle enough that it has been debated ever since as to whether he actually answered EPR's argument or merely changed the subject. The key move in Bohr's reply was to challenge the EPR criterion for elements of reality itself. EPR had said, if you can predict the value of a property without disturbing the system, that property is real. Bohr said, in quantum mechanics, you cannot meaningfully speak of a property of a system in isolation from the experimental arrangement used to measure it. The particle and the apparatus form an indivisible whole. You cannot abstract the particle's properties from the context in which they are observed. There is no view from nowhere. This is the heart of what Bohr called complementarity. It is not that the particle has a spin and measurement reveals it. It is that the spin is defined only within a measurement context. Asking what spin the particle has in the absence of any measurement is not a question that quantum mechanics, as Bohr understood it, is equipped to answer. And Bohr's position was that this is not a deficiency of the theory, but a deep feature of nature itself, applied to EPR. Yes, you can predict the spin of the second particle by measuring the first, but the prediction is only meaningful relative to a specific measurement context. And since the two particles are part of one quantum system, the choice of what to measure on the first particle is part of the total experimental arrangement that applies to the whole system, not just to the particle you directly touch. The influence is not a signal traveling through space. The two particles are, in some sense, still one system, even when they are physically separated. This is both illuminating and, if you stare at it long enough, slightly vertiginous. It does not say that measurement sends a signal. It says that the clean division Einstein assumed, this particle here, that particle there, each with its own independent properties, is itself not a property of the world. The division is something we impose. The world does not honor it. Einstein was not satisfied. He respected Bohr's answer. He always respected Bohr, but he did not believe it closed the case. He thought Bohr was restating the strangeness in different language rather than explaining it. And the two men, who had debated face-to-face in Brussels and Copenhagen and everywhere their paths crossed, were now debating on paper in published journals, each restating the same fundamental disagreement in increasingly careful language. Paul Ehrenfest, who had known both men well and served as a kind of living bridge between them, found the whole exchange almost unbearable. He cared about both Einstein and Bohr. He understood both of their positions deeply enough to see why neither could convince the other. He wrote letters to both of them. He tried to articulate what each was actually saying to the other, whether they were hearing it. Ehrenfest did not live to see the argument's resolution. He died in 1933, 2 years before the EPR paper even appeared. But his anguish at watching the two people he most admired in physics be unable, for all their brilliance, to find common ground, is itself a small piece of the human texture of this story. And then, in a way that is almost eerie in retrospect, the argument simply stopped. Not because it was resolved, not because either side gave way, but because the physics community, by and large, decided that it could not be resolved, that it was a matter of interpretation and philosophy, not of measurement and experiment, that whatever Bohr and Einstein were disagreeing about, it was not the kind of thing physics could settle. For nearly 30 years, from 1935 to 1964, the debate was effectively shelved, not forgotten exactly. Physicists still had opinions about it. Some preferred Bohr's complementarity, which had become more or less the orthodox view, what was sometimes called the Copenhagen interpretation. Others were uneasy with it, as Einstein and Schrödinger had been. A few, like the physicist David Bohm, developed full alternative theories incorporating hidden variables, theories that reproduced quantum mechanics predictions perfectly while maintaining a more classical, realist picture of underlying reality. But the consensus held that none of these alternatives could ever be distinguished from standard quantum mechanics by experiment. The question was considered untestable. It sat in the part of physics that borders on philosophy, and the working physicist's attitude was largely, pick the interpretation that helps you sleep and get on with calculating. This, in the story we are telling, is the 30-year silence, and it is important to understand how complete it was. Some of the greatest minds in physics agreed, and thought the agreement was permanent, that this particular question could never be answered by experiment, that nature would simply not give you the measurement you needed to decide between local realism and the quantum description. It was as if the universe had drawn a curtain over its own nature and said, "You can know the predictions, but not the truth behind them." The silence was not nothing. Things were happening during those 30 years. The technical apparatus of quantum field theory was being built. The practical machinery of nuclear physics and semiconductor physics was being refined into technologies that would reshape the world. The uncertainty principle was being used productively and routinely, without anyone needing to worry about what it meant philosophically. Bohr's Copenhagen framework was not just a philosophical position, it was, for most physicists, a permission to stop asking unanswerable questions and get to work. But somewhere in the background, the question waited. And in 1964, in the least likely of circumstances, it came back. John Stuart Bell was a Northern Irish physicist who worked at CERN, the particle physics laboratory near Geneva. His professional work was on the detailed technical machinery of quantum field theory, accelerator physics, particle interactions, the hard mathematical core of the discipline. He was not a philosopher, he was not a dreamer. He was a precise, meticulous, technically gifted physicist who also happened to have read the EPR paper very carefully and found that he could not let it go. Bell had a sympathy for Einstein's position that was somewhat unusual among physicists of his generation. He found local realism more intuitively satisfying, more physically sensible than Bohr's complementarity. He was not entirely convinced that the Copenhagen interpretation was the last word. He was, in a quiet way, on Einstein's side, and it was precisely because of this sympathy that he set out to give Einstein's intuition the most rigorous possible examination. What Bell did in a paper published in the journal Physics in 1964, a relatively obscure journal, which meant that the paper initially flew mostly under the radar, was to ask a very precise question. He took the class of theories that Einstein had implicitly been advocating for. Theories in which particles carry predetermined values, in which the outcomes of measurements are governed by hidden variables that quantum mechanics does not see, and in which influences do not propagate faster than light. Local hidden variable theories. And he asked, what are the constraints that any such theory must satisfy? The answer was Bell's inequality, a mathematical bound, a number. Bell proved that if local hidden variables exist and govern the behavior of entangled particles, then the statistical correlations between measurements made on those particles cannot exceed a certain value. No matter what the hidden variables are, no matter how cleverly the theory is constructed, as long as it is local and realist in Einstein's sense, the correlations are bounded. The inequality names that bound precisely. And then Bell showed the other half of the argument. Quantum mechanics predicts correlations that exceed the Bell bound. The two frameworks, local realism and quantum mechanics, make predictions that overlap for many experiments but diverge for specific ones. The measurement angles, the specific statistics you collect. Bell worked out exactly what you needed to measure and how to compare the results, and he showed that the two theories would give genuinely different numbers. Not slightly different, not different in a way you could explain away by imprecision or noise, different in a way that could in principle be tested. The philosophical argument had been turned into arithmetic. The 30-year stalemate had a number attached to it. Bell himself was under no illusions about what this meant for the question he cared about. He had, in some sense, set a trap designed to catch local realism and give it the best possible chance, and the same trap that would, if quantum mechanics was right, spring shut on Einstein's beloved picture of the world. Bell did not know which way the trap would close. He hoped, somewhere in the honest part of himself, that local realism would survive, that Einstein would be vindicated, that the particles would turn out to carry their properties all along, that the correlations would turn out to be like the two envelopes sealed at the source, and that the universe would turn out to be, at bottom, sensible and local and real in the way that everything before quantum mechanics had assumed. He published the paper. He continued his work at CERN. He lectured and wrote and thought, and he waited to see what the experiments would show. The experiments took time, not because physicists moved slowly, but because actually performing a Bell test cleanly and convincingly required generating entangled particles reliably, measuring them with sufficient precision, and ruling out every alternative explanation with sufficient care. The technical requirements were considerable. Clauser's 1972 experiment with Stuart Friedman at Berkeley had given the first real answer. Quantum mechanics wins. The correlations violated Bell's inequality. But the locality loophole remained, as Clauser and everyone who examined the experiment carefully acknowledged. And then came Aspect in Orsay between 1981 and 1982, switching the polarizer settings while the photons were in flight, closing the locality loophole with a precision and care that made the results very difficult to argue with. Quantum mechanics won again, local realism lost again, and this time the locality loophole was sealed. There were still, for the extremely careful, other technical gaps. Experiments in physics are never perfect. Every real measurement involves finite efficiency, finite detector precision, finite isolation from the environment. And for some years after Aspect's experiments, the extremely careful still pointed to these remaining gaps. Not as a way of saving local realism from its fate, most physicists by this point had accepted the verdict, but because the gaps were real and a truly complete experimental test requires closing all of them simultaneously. This is a part of the story that is easy to underestimate. The gap between a convincing experiment and a loophole-free experiment in the technical sense is not a trivial one. It required decades of refinement, of improvements in detector efficiency, of new methods for generating entangled photons and entangled atoms, of more sophisticated ways of choosing measurement settings at random to prevent any possible coordination. Anton Zeilinger, working in Vienna, was one of the central figures in this long campaign. Zeilinger's group did not just perform Bell tests. They used entanglement to demonstrate quantum teleportation, which sounds like science fiction, and is entirely real in its carefully constrained meaning, the transfer of quantum state information from one particle to another using an entangled pair as a channel. They used entanglement for quantum cryptography, protocols for exchanging information with security guaranteed not by the complexity of a mathematical problem, but by the laws of physics themselves. Zeilinger's work turned the once philosophical argument about entanglement into the foundation of a technology that did not exist before Bell's paper opened the door. And it was in 2015 that 3 independent groups, one at Delft in the Netherlands, one at NIST in the United States, one in Vienna, performed what are called loophole-free Bell tests. Experiments that closed simultaneously both the locality loophole and the detection loophole, the gap that arises when your detectors do not catch every photon and you have to worry about whether the ones you missed might have behaved differently. All 3 experiments using different methods and different physical systems produced the same result. Bell's inequality was violated. Quantum mechanics was right. Local realism was wrong. And now there were no technical loopholes left to point to. The question that Einstein and Bohr had argued about in Brussels in 1927, the question they had fought over at every conference and in every letter, and in the pages of Physical Review in 1935, the question the physics community had set aside as permanently unanswerable for 30 years, and the question that Bell had turned into a number in 1964, that question had been answered. Not philosophically, experimentally, with a number. And on the 4th of October 2022, the Nobel Committee in Stockholm made official what the experiments had already established. The Nobel Prize in Physics was awarded jointly to Alain Aspect, John Clauser, and Anton Zeilinger for experiments with entangled photons, establishing the violation of Bell inequalities and pioneering quantum information science. 3 names, 3 physicists who had carried the experimental program from its first tentative steps to its conclusive end. And behind them, not named but present in every syllable of the citation, the names of the 2 men whose argument had made the whole thing necessary, Einstein and Bohr. The Nobel citation is careful about what it claims. It does not say quantum mechanics is true. That was already known. It says that these experiments established the violation of Bell inequalities. It says these men pioneered quantum information science. The reward was for the experiments themselves and for the practical harvest that grew from them. A new field, new technologies, new ways of processing and transmitting information that did not exist before the Foundation's question was taken seriously. Which brings us to the verdict itself. What does it mean? Local realism is false. That is the experimental result. Bell's theorem says that any local hidden variable theory must satisfy his inequality. The experiments show that the inequality is violated. Therefore, no local hidden variable theory can be correct. Einstein's specific hope that particles carry predetermined values, that the correlations between entangled particles are like two envelopes packed at the source, that no instantaneous influence connects them, that hope is ruled out, not by argument, by measurement. But the verdict is more precise than Einstein was wrong, and precision matters here. Local realism is a conjunction of two things: locality, the requirement that influences do not propagate faster than light, and realism, the requirement that physical properties have definite values independent of measurement. Bell's theorem and the experiments tell us that this conjunction is false. At least one of the two must go, but they do not tell us which one. Most physicists accept that what fails is the naive version of realism, the assumption that particles have definite properties before measurement. Bohr's complementarity in this reading was tracking something real. The world is not a collection of objects with fixed properties waiting to be discovered. Properties are contextual, defined by and within measurement situations. But there are physicists who take seriously the possibility that what fails is locality instead, that the world is, at a deep level, non-local, genuinely connected across distances in ways that look strange but are real. Bohm's hidden variable theory, for instance, is explicitly non-local. It maintains something like realism but surrenders locality. Bell's theorem does not close this door. And there is one more thing absolutely critical that the verdict does not say. It does not say that information travels faster than light. The correlations between entangled particles are real. When you measure one and then compare results with the person who measured the other, the comparison shows a correlation that no local theory can explain. But, and this is a precise physics language, but you cannot use this correlation to send a message. The result of each measurement taken alone looks completely random. You cannot control what result you get. You can only discover the correlation after the fact by bringing together the two sets of results through an ordinary classical channel, a phone call, an email, a radio signal, that travels no faster than light. Einstein's special relativity, his great achievement, the framework built on the invariance of the speed of light, that survives intact. The no signaling theorem holds. Nothing travels faster than light. What fails is not relativity. What fails is the assumption Einstein made on top of relativity that if nothing travels faster than light, then distant particles cannot be correlated in any way that requires immediate mutual influence. That assumption, reasonable as it sounds, turns out to be wrong. The universe is stranger than the assumption allows, but it is not stranger in a way that lets you send a message backward in time or outpace a photon. This is one of the most important things the experimental program established, and it is also one of the things most often lost in popular accounts of quantum mechanics. The universe answered the question in a way that was neither the simple Einstein answer nor the simple anti-Einstein answer. It was subtler. Local realism is gone, but the prohibition on faster-than-light signaling is intact. The world is non-local in its correlations, but not in its causal structure. The two things, correlation and causation, had been quietly assumed to always travel together, and it turns out they do not have to. Bohr was right that quantum mechanics is complete and correct in its predictions. Right that the Copenhagen framework, with all its conceptual strangeness, was tracking something real about how nature behaves. Right that you cannot speak of a particle's properties in isolation from the measurement context. Einstein was wrong about local hidden variables, wrong in his specific hope that the correlations would turn out to be the sealed envelope kind, written in at the source, requiring no connection between the particles after separation. But Einstein was also right about something, and this is the part of the verdict that is most often missed. His EPR paper, the paper that was meant to demonstrate the incompleteness of quantum mechanics, did not achieve its intended purpose. Quantum mechanics turned out to be complete in the relevant sense. But the paper did something else, something arguably more important. It named entanglement as the central feature of the theory. It forced the physics community to look directly at what quantum mechanics was actually saying about correlated systems. It drew the map of the territory that Schrödinger named and Bell measured, and Aspect and Clauser and Zeilinger spent their careers exploring. Without EPR, there is no Bell's theorem, at least not in the form it took. Without Bell's theorem, there are no Bell tests. Without Bell tests, there is no experimental confirmation of entanglement as a real physical phenomenon. Without that confirmation, the technologies that Zeilinger's group built, quantum cryptography, quantum teleportation, the foundations of quantum computing, have no ground to stand on. The paper Einstein wrote to argue that quantum mechanics was missing something turned out to seed the experimental and technological program that proved it was not. The wrong paper launched the field that vindicated the theory it meant to challenge. There is a particular kind of intellectual generosity in that outcome. The universe did not simply correct Einstein and move on. It used his argument, the precise, careful, logically tight argument he built, as the lever that pried open the question, turned it into a measurement problem, and eventually produced the answer. His instinct that entanglement was the heart of the matter was exactly right. He was wrong about what it meant, wrong about the conclusion it implied, wrong in his hope that hidden variables would save the day. But he was looking at the right thing. And so we arrive at the hinge. 1964. The arguments were old by then. Einstein had been dead for 9 years. Bohr had died in 1962, still drawing on blackboards, still circling the same question. The Fifth Solvay Conference was nearly 40 years behind everyone. The EPR paper had been sitting in the archives of physical review since 1935, read, cited, disputed, and ultimately set aside with a kind of collective shrug, because physicists had arrived by long consensus at a quiet and somewhat uncomfortable conclusion. The question could not be tested. That was the agreement, not spoken loudly, not written up as a formal declaration, but absorbed into the culture of physics as a working assumption. You could argue about hidden variables over dinner, you could write thoughtful papers about complementarity and local realism and what it might mean for something to have a definite position before anyone looked at it. But you could not do an experiment. The two interpretations, Bohr's, in which quantum mechanics is complete and a particle has no definite properties until measured, and Einstein's, in which the theory is incomplete and particles carry hidden predetermined values that the theory simply fails to describe, made identical predictions for every measurement anyone could perform. They agreed on every number. They disagreed only on the story behind the numbers. And physics, as most physicists would tell you, is in the business of numbers. So the argument was filed under philosophy. And there it might have stayed, gathering the particular kind of dust that philosophy gathers in a physics department, if a quiet man from Northern Ireland had not sat down in 1964 and done something that seemed, at first, almost impossible. His name was John Stuart Bell. He worked at CERN, the great European particle physics laboratory outside Geneva. But the problem he turned his attention to had nothing to do with his official work. He came back to it, he would say later, out of a private dissatisfaction, a feeling that the argument had been closed too quickly, that the philosophical gesture of declaring it untestable was itself a kind of surrender. He was, in a quiet way, on Einstein's side. He genuinely hoped, that if you were careful enough, you might find a way to give local, hidden variables a fighting chance. He wanted to vindicate Einstein. What he found instead was the theorem that trapped Einstein's hopes in an equation. Bell's paper was published in 1964 in a journal called Physics. It was a small, relatively obscure journal and the paper itself was not obviously immediately recognized as the thing it turned out to be. The title was On the Einstein-Podolsky-Rosen Paradox. Modest, precise, a paper about a 29-year-old argument. You can imagine it sitting on library shelves in the mid-1960s waiting. The idea at the center of it was elegant in the way that genuinely important ideas tend to be. Not complicated, but clear in the way that makes you wonder why nobody thought of it before. Bell asked a very careful question. He asked, if Einstein is right, if particles really do carry hidden variables, predetermined answers to every question you might ask about them, what does that force us to conclude about the correlations between entangled particles? What numbers does local realism actually predict? This takes a moment to feel. So let's go slowly. When two particles become entangled, when they interact in such a way that they form a shared quantum state, something strange happens when you measure them. You measure the spin of one particle along one axis and you get a result. Then you measure the spin of the other particle far away along some other axis and you get another result. Do this many times and you build up a pattern of correlations. The two results are related to each other in a way that depends on the angle between your two measurement axes. When the axes are aligned, the results are perfectly correlated. As you change the angle between them, the correlation changes in a specific way, a smooth curve described by quantum mechanics. Now, Einstein's position was that this correlation exists because the particles were carrying hidden information all along, like two gloves from the same pair, packed into separate boxes and shipped to opposite ends of the world. When you open your box and find a left glove, you instantly know the other box contains the right glove. No mystery, no influence at a distance. Just information that was there from the beginning, hidden in the packaging. Bell's question was, can that explanation, the glove explanation, the hidden variable explanation, reproduce the exact pattern of correlations that quantum mechanics predicts? And he found that it cannot. Not because hidden variables are logically impossible, not because the mathematics breaks down, but because there is a specific feature of the correlation curve, the precise way the correlations behave as you vary the angle between the measurement axes, that cannot be reproduced by any local hidden variable theory. If the particles are carrying predetermined answers, the correlations must stay within a certain bound. Bell worked out exactly what that bound is. He wrote it down as an inequality, a mathematical statement that any local realistic theory must satisfy, and quantum mechanics predicts violations of that inequality. This was extraordinary, not because it proved Bohr right, not yet, not from the mathematics alone, but because it meant the two camps were no longer making the same predictions. For certain arrangements of the experiment, certain combinations of measurement angles, local hidden variables and quantum mechanics predicted different numbers. Numbers you could, in principle, measure. The philosophical argument had a number attached to it. Bell himself described this quietly. He was not a man given to drama. He noted that his result meant the question was now empirical rather than merely interpretive. You could go into a laboratory, you could build an apparatus, you could measure entangled particles along carefully chosen angles, and then you could ask, do the correlations violate Bell's inequality, or don't they? If they don't, if the correlations stay within the bound Bell calculated, then hidden variables are still in the game. Local realism survives. Einstein's intuition had room to breathe. If they do violate it, if the correlations exceed the bound exactly as quantum mechanics predicts, then no local hidden variable theory can be right. The particles are not like gloves. Whatever is happening between them cannot be explained by information they were carrying all along. 30 years of philosophy, 30 years of this cannot be tested, and here was a clear, clean experiment waiting to be done. Bell was sympathetic to the side he was about to defeat. This matters. There is something deeply moving about the fact that the man who gave Einstein's hope a fighting chance was also the man who built the cage around it. He was not trying to kill local realism. He was trying to test it fairly. He gave it every reasonable benefit. He constructed the inequality precisely to make the test as gentle and as rigorous as possible. And then he handed the question to the experimenters. It would take 8 more years before anyone could build the apparatus to ask it. The first serious attempt came from John Clauser. He was a graduate student, then a young postdoc, working at Berkeley in California. And he had read Bell's paper with the kind of excitement that occasionally grips a physicist who feels that everyone else in the room has missed something important. Most of the community had not taken Bell's theorem seriously as an experimental challenge. The prevailing mood was still that the question was somehow settled, or at least not urgent. Clauser disagreed. He worked with Stuart Friedman. Together they built an experiment using calcium atoms that, when excited to a certain energy level, emit pairs of photons in a correlated way. The photons fly off in opposite directions, and their polarizations are linked. The correlation between the polarization measurements made at 2 separate detectors could then be compared to Bell's inequality. In 1972, Clauser and Friedman published their result. The data violated Bell's inequality. Quantum mechanics was right. Local hidden variables could not explain what they saw. It was a significant result. But the physics community wanted more, not because they doubted the experiment. Clauser and Friedman were careful, and the result was real, but because there were what you might call loopholes. Not loopholes in the logic, loopholes in the experimental setup. Ways that a stubborn defender of local realism could, in principle, object. The most important loophole was this. In the Berkeley experiment, the orientations of the polarizers, the angles along which the photons were measured, were set in advance before the photons were even produced. This meant, technically, that the hidden variables could have known the measurement settings ahead of time. The information could have been encoded in the particles when they were created, coordinated with the detector settings, without any actual influence at a distance. It was a stretch. It was a very unlikely explanation. But science is not in the business of dismissing unlikely explanations on grounds of taste. The loophole existed. It needed closing. Enter Alain Aspect. He was working at the University of Orsay in France in the early 1980s, and he had set himself precisely this task. The challenge he accepted was audacious: close the locality loophole by switching the orientation of the polarizers while the photons were in flight. Think about what that requires. The photons leave their source and travel toward their respective detectors. During the time they are traveling, a matter of nanoseconds, a few billionths of a second, the detector settings have to change. The choice of measurement axis has to be made after the photons are already on their way, so quickly that no signal, not even a signal traveling at the speed of light, could carry the information from one detector to the other in time to coordinate the results. It is, when you picture it, a remarkable piece of experimental engineering. Aspect's team had to build a system that could switch the polarizer orientations in nanoseconds, randomly, while photons were literally in transit between source and detector. The distances were small, cutting a few meters, but at the speed of light a few meters is a very short time indeed. The experiments ran in 1981 and 1982. The polarizers switched, the photons landed, the correlations were measured, and the correlations violated Bell's inequality by a wide margin, cleanly, unmistakably. The locality loophole was closed. Whatever was happening between those photons, it could not be explained by information the photons had carried from the start. The results at one detector were correlated with the results at the other in a way that nothing predetermined, nothing locally stored could account for. the universe was not sending hidden messages in advance. Something stranger was going on. Aspect's work was received as decisive by most of the community. The conversation about Bell tests shifted from that point toward increasingly precise confirmation, closing additional loopholes, extending the experiments over greater distances, testing under more and more rigorous conditions, and that is where Anton Zeilinger entered the story. Zeilinger's group, working in Vienna and later in a number of landmark experiments across distances large enough to satisfy even the most persistent objector, did not simply confirm what Clauser and Aspect had established. They extended it. His team pioneered what is called quantum teleportation, not the science fiction kind, not the matter transmitted from here to there kind, but the real and genuinely remarkable ability to transfer the quantum state of a particle from one location to another, using entanglement as the channel and a conventional classical signal to complete the process. They worked on quantum cryptography, the use of entanglement to create encryption keys that cannot be intercepted without detection because any eavesdropping disturbs the quantum state and announces itself. These were not merely demonstrations. They were the first steps of a technology, a field called quantum information science, that grew directly from taking entanglement seriously as a real, exploitable physical phenomenon. It is worth pausing on that. The argument began as philosophy. Bell turned it into an experiment. Clauser and Aspect and Zeilinger ran the experiments. And somewhere in the act of doing so, the once abstract discussion about what was really real became the foundation of an actual engineering discipline. Entanglement, which Einstein had named spooky action at a distance and dismissed as evidence that something was wrong with the theory, turned out to be a resource, a thing you could harness and build with. The spookiness was not a flaw, it was a feature. But there were still loopholes, not in Aspect's work specifically, but in the broader program of Bell tests. Each experiment was rigorous, but each left at least one crack at the detection loophole, where detectors did not catch every photon, and one could argue the detected subset was somehow special. The locality loophole, now largely closed, but still discussed in formal terms, and the freedom of choice loophole concerning whether the settings were truly random or could somehow be correlated with the hidden variables. Individually, each objection was implausible. Together, they represented the last shelter for anyone who still wanted to hold on to local realism without abandoning their scientific respectability. In 2015, several groups working independently, at Delft in the Netherlands, at NIST in Colorado, and in Vienna, performed what became known as loophole-free Bell tests. These were experiments designed to close the locality loophole and the detection loophole simultaneously in the same run, so that no combination of the known objections could account for the result. The data from all three groups agreed Bell's inequality was violated, loophole-free. There was, after 2015, no remaining scientific shelter for local realism. The question that Einstein and Bohr had argued about in Brussels in 1927, the question that the EPR paper had sharpened into a precise logical challenge in 1935, the question that Bell had transformed into a measurable number in 1964, the question that Clauser and Friedman had first tested in 1972 and Aspect had driven home in 1981 and 1982, and Zeilinger had extended across distances and into technology, that question had an answer. And then, on October 4, 2022, the Nobel Committee in Stockholm made it official. The Nobel Prize in Physics for 2022 was awarded jointly to Alain Aspect, John Clauser, and Anton Zeilinger for experiments with entangled photons, establishing the violation of Bell inequalities and pioneering quantum information science. Bell himself had died in 1990, too early to see this. Clauser had waited decades, working through periods when the broader community showed little interest. Aspect had done his most important work as a relatively young researcher, then watched the field he helped to found grow into something far larger than any of them had imagined. Zeilinger had spent a career building the technologies that emerged from treating entanglement as real and useful rather than puzzling and problematic. The Nobel was not just a recognition of three physicists, it was a recognition of the long, strange, patient journey from a philosophical argument between two friends to a verified fact about how the universe works. So what does it mean? This is the question that deserves the most careful answer, because it is very easy to give the wrong one. The wrong answer is the simple one. Einstein lost. You will hear it. It has a certain satisfying cleanness, but it is not accurate, and it does not do justice to what actually happened. Here is the careful version. Bell's theorem and the experiments that tested it ruled out what physicists call local realism. That phrase contains two ideas. Locality is the principle that an event in one place cannot instantaneously influence an event in a distant place. That causes must travel, and nothing travels faster than light. Realism in this technical sense is the assumption that physical quantities have definite values before they are measured, that the particle had a specific spin or a specific polarization whether or not you looked at it. Local realism is the combination. Particles carry predetermined values, and those values are set locally without any instantaneous influence at a distance. This was Einstein's preferred picture. This is what the hidden variables were meant to provide. And this is what the experiments ruled out. But notice, the experiments ruled out the combination. They tell us that we cannot have both locality and realism in the classical Einstein-preferred sense. At least one of them has to give. What they do not tell us is which one. The physics community has not fully settled this. Some interpretations of quantum mechanics keep locality and give up a naive realism. Some keep something like realism and give up strict locality. The debate about what exactly to abandon is, in a sense, still alive, but it is a debate within the confirmed framework that local hidden variables are excluded. Einstein was wrong about local hidden variables. That is the clear, clean result. The particles are not like gloves. They do not carry predetermined answers to every possible question. Whatever account we give of them must include genuine indeterminacy or genuine non-locality, or both. And yet, Einstein was not wrong about entanglement. He was not wrong to identify it as the central, strange feature of quantum mechanics. The EPR paper, which he wrote to argue that quantum mechanics was incomplete, correctly isolated entanglement as the thing that needed explaining. He handed the community the question in its sharpest form. The fact that the answer came back differently than he hoped does not diminish the quality of the question. And there is one more thing that Einstein was not wrong about, and it deserves to be said clearly because it is often lost in the drama of Einstein versus Bohr. Einstein insisted throughout his life that entanglement could not be used to send signals faster than light. He was right. The correlations between entangled particles, the violations of Bell's inequality, the strangeness of the results, they do not allow any information to travel faster than light. When aspects photons landed at their detectors on opposite sides of the experiment, neither detector showed anything strange. Each detector saw a random sequence of results. The correlation only appeared when the two sequences were later compared, when someone carried the data from one detector to the other by ordinary means and looked at both sets together. The strangeness is in the correlation, not in the individual results. And correlations cannot be used to send a message. 2. Einstein's relativistic prohibition on superluminal signaling survives, intact and unchallenged. The universe is deeply strange in a way that Einstein disliked, but it is not strange in the way that would have allowed you to use entanglement as a telephone to the past or a signal that outpaces light. That particular worry, at least, was never warranted. Einstein's intuition on that specific point was exactly right, and it remains right. So the verdict, stated with the care it deserves, is something like this. The universe is not locally realistic in Einstein's sense. Particles do not carry hidden predetermined values. The correlations between entangled particles cannot be explained by anything local and pre-existing. Whether you describe this as a failure of locality or a failure of naive realism, whether you are a physicist who prefers to say the world is genuinely non-local, or one who prefers to say that properties are genuinely indeterminate until measured, you are committed to something that Einstein would have found deeply uncomfortable. Bohr was right that quantum mechanics is complete. The theory was not missing anything. The strangeness was not a symptom of ignorance. It was a description of reality, but Einstein was right that entanglement was the heart of it. He was right that it was the feature most in need of examination. He was right that no superluminal signal passes between entangled particles. And he was, in the deepest sense, the one who forced the argument to its conclusion, even though the conclusion was not what he wanted. Neither man was simply right. Neither man was simply wrong. They were both, in the ways that mattered most to them, looking directly at something real. And both of them died without knowing the answer. Bohr died in November 1962, still drawing on his blackboard. Einstein had died in 1955, Bell died in 1990, still hoping that someone would find a subtlety he had missed, still uncertain whether his theorem had truly closed the door on local realism or merely made it harder to open. The three experimenters who earned the Nobel Prize in 2022, Aspect, Clauser, Zeilinger, did the work across decades and in relative quiet, building apparatus and measuring correlations in experiments that much of the physics community considered settled long before they were officially confirmed. The Nobel Prize came in 2022, 95 years after the Fifth Solvay Conference convened in Brussels, 87 years after the EPR paper appeared in Physical Review, 58 years after Bell published in that small journal called Physics. The question moved slowly in the way that deep questions do. It moved from a lobby at the Hotel Metropole in Brussels, where Einstein and Bohr argued over breakfast, to the pages of a correspondence that spanned decades, to a 9-page paper in an obscure journal, to a laboratory in Berkeley, to an optics table in Orsay, to a long series of experiments in Vienna, to Stockholm. The journey took nearly a century, and when it arrived not as a repudiation, but as a completion. There is something I want you to sit with for a moment, if you are still awake. Both of these men, Einstein and Bohr, were trying to understand the same thing. Not quantum mechanics in its technical details, not the equations or the predictions or the calculations. Something deeper than that. They were trying to understand what reality is, what the world is like when no one is looking at it, whether the moon, as Einstein famously put it, exists when no one is looking at it, whether the universe is, at its foundations, a place of definite things or a place of genuine indeterminacy resolved into specificity only by observation. That is a very old question. It is older than physics. It is older than science. Philosophers had been arguing about it in different vocabularies for thousands of years. But what Einstein and Bohr did, and what Bell and Clauser and Aspect and Zeilinger did after them, was turn it into something that could be measured. They found a way to ask the universe directly, in a language the universe could answer in numbers. That is extraordinary. Whatever the answer turns out to be, and we have it now, at least in the form of ruling out one very specific possibility, the fact that the question was answerable at all is itself remarkable. The fact that the deep structure of the world, the question of what is real before anyone looks, could be reached by careful people with photons and polarizers and very precise clocks, that is not obvious. There was no guarantee it would work out that way, and yet it did. You are lying somewhere in the dark, or sitting, or letting this wash over you in whatever quiet you have found tonight. and the universe around you is, right now, not locally realistic in Einstein's sense. The particles that make up everything in your room, everything in your body, every photon coming from the lamp that is still on, every atom in the blanket, every electron in the circuitry of whatever device is playing this, they are not carrying hidden messages, predetermined answers, a pre-written story of what they will do when observed. The world is genuinely open in a way that Einstein could not accept and Bohr could not fully explain, and Bell learned to measure, and the experiments finally confirmed. This is not a comforting thought, and it is not an unsettling one. It is simply what is true. The universe at its finest grain is not like a clockwork mechanism with hidden springs. It is something stranger and in a way more generous, more open to what happens next, more genuinely alive in each moment than the classical picture ever allowed. And the two men who argued about it most fiercely, most carefully, most lovingly, because it was, in the end, a friendship dressed up as a dispute, they both saw something real. They were both looking at the right thing. They just could not agree on what it meant. Bohr, on the last day of his life, was still trying. The blackboard in his study still bore Einstein's drawing. He had been thinking about that light box for 32 years. Einstein had been dead for 7 years, and Bohr was still not finished with the argument. You can read that as stubbornness, or you can read it as the deepest kind of intellectual love, the love that says, this question matters so much, this person's challenge was so good, that I will keep turning it over for the rest of my life, not because I doubt my answer, but because the question deserves that kind of care. When Bohr died in November 1962, the blackboard was still there. No one erased it. And you have to imagine, if you are the kind of person who imagines these things in the quiet before sleep, what it was like for the people who came into that room and saw it, the drawing of the box with the shutter, the box that was supposed to trap a single photon and pin down its energy and its time of emission and break the uncertainty principle, the box that Bohr had spent a sleepless night with and defeated using Einstein's own theory of gravity, still there, still being thought about. The argument still warm. That blackboard is, to my mind, one of the most beautiful images in the history of science, not because it shows victory or defeat, because it shows the shape of a question that mattered too much to put down. Two brilliant people, disagreeing across decades about the nature of reality itself, each one sharpened by the other's objections into a precision they might not have achieved alone. The rivalry was not what made the science possible. The friendship was. And then 60 years after that room in Brussels, 60 years after those 29 people sat for a photograph with 17 Nobel Prizes among them and the whole future of physics unsettled in the air, 3 experimenters stood in Stockholm and accepted a prize for showing what the universe's answer was. The answer is this: reality is not locally realistic. At least one of the things Einstein insisted on is false. The question of which one, whether locality holds and realism fails, or whether something else gives, that is still being argued, gently, carefully, in the way that good questions deserve to be argued. But the specific hope that Bell tested, the hope that particles carry hidden variables and correlations, are just shared information planted at the source. That hope is excluded. The experiments close the door. What is left is not emptiness. What is left is something more interesting. The violation of Bell's inequality is, when you really let it land, one of the strangest verified facts in all of science. It says that 2 particles, separated by any distance you care to name, can be correlated in a way that no local hidden variable can explain. The correlation is real. It is measured. It is confirmed loophole-free by 3 independent groups in 2015 and awarded the Nobel Prize in 2022. And yet it cannot be used to send a signal. The strangeness is there in the data, unmistakable, And it is, at the same time, curiously sealed. You cannot reach through it. You cannot use it to communicate faster than light. The universe allows this peculiar non-local correlation and simultaneously prevents you from exploiting it to violate causality. It is almost as if the universe arranged things so that the strangeness is real and total and the consequences are safe. As if reality can be genuinely strange without becoming incoherent. That balance, deep weirdness carefully contained, is one of the things that makes physics feel at its best, not like a cold inventory of mechanisms, but like the discovery of something almost artful. Einstein, who believed the universe must be rational and not given to dice games, was wrong in his specific prediction. But his instinct that reality had a deep coherence, that the strangeness would resolve into something you could understand even if it took a century, was not entirely misplaced. The universe is strange, but it is not arbitrary. It is strange in a structured, consistent, measurable way. You can write down the inequality it violates, and it will always violate it by exactly the right amount, everywhere, every time. There is something almost restful in that if you let it settle. The argument is over in the specific sense that local realism is excluded and the experiments are done. The deeper questions, what exactly we should say about the nature of reality, which interpretation of quantum mechanics captures something true rather than merely something useful. Those questions go on. They will probably go on for a long time, but they go on in a different landscape now. A landscape in which we know with the precision of loophole-free Bell tests and Nobel Prizes what the universe is not. And knowing what something is not is sometimes the most useful form of knowledge there is. It clears the ground. Bohr spent decades clearing the ground, and Einstein spent decades pushing back against the clearing. What the experiments showed in the end is that Bohr was right about the ground, but Einstein's pushing was what made the work real. You need someone to push.
I want to go back now to where we started tonight. That blackboard, the room in Copenhagen, November 1962, a drawing in chalk still there on the board. Einstein's photon box, drawn in Einstein's absence, the argument Bohr had lived with for more than 3 decades. The box with the shutter, the spring scale, the idea that you could weigh light and catch the uncertainty principle in a contradiction.
Bohr had answered it. He had answered it the night Einstein proposed it back in 1930 using Einstein's own theory of gravity in a move so elegant it made the physicists watching it feel the hair stand up on the back of their necks. He had answered it and won in every technical sense. And yet, he kept it on his blackboard. Not because he was unsure, not because he thought Einstein might still be right somewhere in the mathematics, but because the question, the shape of Einstein's mind, the quality of his objection, the depth of what he was reaching for when he built that thought experiment, deserved to stay visible, deserved to be honored, deserved to be kept in the room. That is not what scientific rivalry looks like in the way we usually tell the story. In the way we usually tell it, someone wins and someone loses, and the winner gets the prize, and the loser's ideas get corrected out of the textbooks. But this is not what happened here. What happened here is that 2 remarkable people cared so much about the same question for so many decades with such precision and such respect that the question itself became the most important thing, more important than either of them being right. And the universe, when it finally answered in a way that gave them both something. Bohr. The theory is complete, and entanglement is real, and the experimental program built on your framework confirmed it with the Nobel Prize 95 years after you first squared off in Brussels. Einstein, you were right that entanglement is the heart of it, right that it is the strangest feature, right that it cannot be used to send signals faster than light, and the paper you wrote to challenge the theory turned out to seed the field that proved it.
Neither of them is here to receive that. They did not live to see the experiments. They did not live to see Bell's theorem become a laboratory measurement, or Clauser and Friedman's calcium atoms, or aspects polarizers switching in nanoseconds while photons flew between them, or Zeilinger's teleportation, or the loophole-free tests of 2015, or the ceremony in Stockholm in October 2022. They had to leave with the question still open.
And perhaps that is as it should be. Perhaps the questions that matter most are the ones we do not get to close ourselves. We hand them forward, we build the most precise version we can, we push it as far as we can reach, and then someone else, Bell, working at CERN in 1964, trying to be fair to a man who had been dead for 9 years, picks it up and goes further. That is how it works. That is maybe the most honest account of science there is. Not a march from ignorance to knowledge, but a long, patient relay, question passed hand to hand, each person sharpening it a little more until the day someone finally has the instruments to ask the universe directly. And the universe answers. Wherever you are right now, whatever darkness or quiet you have settled into tonight, that universe, the one Bell measured and aspect confirmed, and Zeilinger built technology from, and the Nobel Committee named in 2022, is the same universe you are lying in, the same non-locally correlated, determinacy-refusing, Bell inequality-violating universe. The particles in your body are not carrying hidden messages. They are open to what happens next in a way that Einstein found impossible to accept, and Bohr spent his life trying to describe. You do not need to understand the mathematics to feel the shape of that. You do not need to have worked through the EPR paper, or Bell's 9 pages, or aspects polarizer switching setup. The shape of it is this: the world is genuinely, verifiably stranger than our intuitions suggest, and 2 people who cared about it more than almost anyone ever has spent their lives in a gentle, decades-long conversation about exactly how strange, and they were both right about the part that mattered most to them. And the answer came in the end, as answers sometimes do, long after the people who most needed it were gone. That is a good thing to carry into sleep, I think. The argument is settled. The question is answered. Local realism is excluded, entanglement is real and verified, and the foundation of technologies that Bohr and Einstein could not have imagined, built from the strange correlated particles they spent their lives arguing about. Bell's inequality is violated everywhere, every time, by exactly the amount quantum mechanics predicted it would be. The Nobel Prize was given on October 4, 2022, to 3 people whose names will stay linked to this story: Alain Aspect, John Clauser, Anton Zeilinger. And somewhere in a room in Copenhagen that probably does not look the way it did in 1962, there is no blackboard anymore. The chalk is long gone. But the question it held, the shape of that argument, the generosity of 2 brilliant minds locked in a decades-long effort to understand the same true thing, that has not gone anywhere. It went into the experiments, into the data, into the Nobel citation, into this quiet account, told slowly, here, in whatever hour of the night you find yourself in. If you have found something worth staying awake for in this tonight, a gentle like or subscribe really does help. Small creators like me rely on it to keep these journeys going, and I am grateful for every one of you who has settled in and listened this far. And if you want to leave a small trace of where you've been, tell me in the comments where you're listening from tonight and what time it is in your corner of the world. I always read them. I like knowing where these words go. The story of Einstein and Bohr is, at its heart, a story about what it looks like when 2 people care about the same question enough to spend their whole lives on it, and about what the universe owes those people, which is not vindication, not for either of them, but an answer, eventually patient and precise and strange enough to honor the depth of the asking. Reality is not locally realistic. The moon exists when no one is looking at it, probably, but the way it exists is stranger than Einstein hoped and stranger than Bohr could cleanly say. And the strangeness has been measured, and the measurement stands. Sleep well, fellow voyager. The next journey keeps until you wake.